It's, well, thank you very much, Ada. So, um, essentially, I'm going to talk about a problem in information theory in general, but specifically in Shannon information theory, using tool information theory. So I'll be starting with mainly recaps. So three first parts will be introductions, I should say. And then I'll delve into the tools I will be using in section 4, and then the actual, um, let's say, work that I've been doing in section 5. So the first part, let's start with this, is where I just review what is Shannon information theory, the basics. So let's start. Um, okay, this is not so important. I will be explaining everything as we go along, but maybe it's good to, this random variable is a capital letter, realization is a small letter, lowercase, and a set will be always calligraphic. I will use this a lot. X to the power n will actually mean a sequence of let's say objects x1 to xn. Um, Whenever you see this or this, it's related to a floor, essentially. This is actually a set of all integers from 1 to the floor of A, or from 1 to A, let's say. Anyway, I think this will be clear in everywhere. So in Shannon information theory, there are quantities which will appear in the theorems. Um, so one of them is entropy. So for a discrete random variable x, the entropy is going to be defined like this. It's like an expectation of the log of the probability mass function. So for continuous variables, you also have another similar expression with a density f. Um, it's not very important to, like, the expression is not very important. That's not what I'm going to use today, but it's just to tell you this is going to be an important quantity, and is going to appear in what is called lossless source coding or lossless compression. It's, imagine you want to compress an image, but you don't want to lose any information. You want to be able to recover exactly the original image without any loss. So we call it lossless compression. Okay, so there is a conditional version of entropy. Um, this is not going to essentially appear much today, but is useful to define the next quantity, which is mutual information, which will be very central. So it's it has this kind of interpretation. So the x and y is actually the decrease of uncertainty that we have due to the knowledge of y. So we don't know the value of x, the realization of x exactly, it's a random variable. But whenever we know the exact value of y, the realization of y, then it decreases the uncertainty about x. And the decrease of uncertainty is essentially this mutual information. So anyways, just for your, let's say, knowledge that, oh, these things exist, but you don't have to remember any of the details here to understand what I'm going to talk about next. So these quantities are always non-negative. Everything is non-negative. The entropy is bigger than the conditional entropy. And the mutual information, as is intuitive, is actually zero if the variables are independent. There is no mutual information. Oh yeah, I didn't say this is the name of I is the mutual information. That's what I've been talking about. And I guess there are just a lot of interesting properties. Maybe I will just quickly say that I will be talking about essentially Shannon theory is about compressing ergodic sources like Markov chains or just i.i.d, a sequence of i.i.d variables. So we will start with quantities like this, where there is a sequence xn. So remember that the notation xn is a sequence of n elements. Yn is also a sequence of n elements. So we will start with this, but then because of the uh, Markov chain property or i.i.d property, we can get a convergence towards some limit quantity that would essentially look like this. And the limit quantity is what we're going to be interested in, is the most important thing. So um, just keep in mind that sometimes there will be sequences, sometimes there will be just like kind of limit distributions or variables. Okay, I think everything will get clear when I start with the definitions now. Oh, just a question. Do you actually see my pointer, like my mouse?
Yes.
Okay, perfect. So, okay, the basic problem in compression is that you have a sequence xn, so n symbols, or sorry, n elements, and I think the best thing is to start with the simplest example, which is i.i.d. So x1, x2, etc. are mutually independent and identically distributed. And this sequence, you use some deterministic function, the encoder, which is going to be denoted as f, and you map xn into an integer between 1 and 2 to the nr, with r being some real number that we will choose later. So you map it to an integer, and then the decoder is going to take that integer, so decoder gn, takes the integer and gives uh, a sequence yn, so n elements again. So before explaining the rest of this slide, I just want to give you an idea. Like essentially what we're doing is that we wonder essentially how many bits, how many zeros and ones we need to encode or to compress the initial sequence, the i.i.d initial sequence. So the number of bits is actually the exponent here. It's n multiplied by r. Why? Because you can have a bijection between the set of integers from 1 to the nr and the set of strings of zeros and ones of length n multiplied by r. Just so that's why we look at this kind of integer um, sets. And so this is like a mathematical formalism to be able to talk about the number of bits, the number of zeros and ones that we need for compression. And there is one last element I need to talk about, which is the distortion function, is d. So yeah, we usually say alphabet, but it just means sets. So set x is where, so x1, the first element of the sequence is in x, x2 as well. All the elements of the sequence xn are in the set x. Same thing for yn in the set y. And so you have a distortion function, which is like an error function, or it counts mistakes in some sense. You could think of it as a distance, as a metric. So the distance or distortion between a sequence xn and a sequence yn is going to be the average. Oh, I forgot the indices here, but it's going to be the average of distance between x1 and y1, the first element, plus distance between x2 and y2, etc. You take the average. Okay, so essentially now the goal is that we don't want the distance between xn and yn to be too big. Otherwise, think about, you compress an image into bits, then you open the file. If you get an image that is very, very different from the original, then you will not be satisfied. So the distortion is there to measure how close the reconstruction yn is actually to the original xn. And so, as is, I think, intuitive, we want to have an upper bound on the expected distance or expected distortion. So this quantity is just yn. I could have written yn, but I just wanted to make it explicit that you take xn, you do the encoder fn, then you do the decoder gn, and you get yn. Now we just don't want this distortion to be too big. So we impose as a target, as a goal, that we want this distortion to be less than d for some real number d. That is going to be the goal. And now you, let's say, you can do a very naive algorithm to compress xn, so naive encoder, naive decoder, which will give you what you want, but it might take a lot of bits, like maybe a 1 GB file for one image, which would be very unfortunate. So the mathematical problem is to reach this constraint, to satisfy this constraint with the smallest possible r, not a real number r. So that is the problem we're going to be looking at. And I will repeat this in the next few slides. So we want to satisfy the constraint to not change the source, like the first sequence, too much, but we want to do that with minimal number of bits, or minimal number r. So there is a theorem that says that the minimum number of bits to reach distortion d, like to satisfy the constraint with a value d, is expressed as this minimum. And notice that this is what I said about limit distributions, or there is no sequence here. There are no sequences here. There is some limit distribution in some sense, that is small p of xy. And the mutual information, it doesn't matter really what the expression is for now. It's just good to know that we have an expression of the optimal r related to some limit distribution p. Okay, so there are some small assumptions, but that's not very, very important. So let's just try to understand, okay, what are we talking about? Just to repeat essentially what I've said in a different way. So let's say I want the distortion, or the distance between xn and yn, to be maximum 0.4. Otherwise, I will not be satisfied. Otherwise, it will be too big. Distance will be too big. So I want the distance to be less or equal to 0.4. So the function me for 0.4, I can go and read the y-axis to know how many, let's say, what is the smallest number r that will allow me to satisfy this constraint. So essentially what I'm saying is that if you want to have a small distance or distortion, then you have to preserve enough information about the original sequence. You cannot remove most of the information from the original sequence using a very small number of bits, like 0.1, for example, for r. That would not work. If you remove too much information, you cannot get a small distortion or a small error or distance. So in order to get small distortion like 0.4, you need at least r equal, let's say, 0.708 or something. You need to preserve enough information so that you can have a small distance. Otherwise, it's not going to work. So yeah, just the intuitive idea. What we're trying to do is we want to find the smallest possible r that will be enough. You preserve enough information so that you have a small distance or distortion. Okay, and now I think that the mathematical details for this are going to become maybe clearer when I show you now the proof in just 2 minutes. We'll go slowly through the proof, so I think it will make sense, inshallah. So I just want to add comments. It's going to be interesting for later, which is that I told you that the encoder and decoder were deterministic functions, but you might think, yeah, why not? Maybe we can make them non-deterministic, so randomized. And actually, it's been shown that it's not useful for this basic problem. This is the first problem, but the answer will be different for other problems. Sometimes randomized encoders, decoders will be useful. Yeah, I just wanted to, I think the most famous result in this field is this one, is when d is equal to 0. So when you want no distortion at all, you don't want, so you want the reconstruction yn to be exactly the same as xn. So in that case, the the small value of r that you need is actually the entropy of x, the entropy essentially of the distribution of every symbol of x. So this is when you don't want to lose any information. You want to preserve everything. Okay, so now let's look at oh yeah, before we go into the proof, I just wanted to mention you can do that for continuous variables, for a Gaussian distribution, for example. And why is that interesting is because actually now I told you what is the optimal R, but I didn't tell you what is the optimal encoder and like a good encoder and a good decoder. And for the Gaussian distribution, the optimal encoder and decoder is actually the JPEG algorithm. You might know if you have images on your computer, they have a JPEG or a JPG extension. That's an algorithm that has been inspired by essentially studying this problem, where we find that uh, for a Gaussian distribution, there is a simple algorithm that gives you the optimal performance. The simple algorithm involves a Fourier transform, a discrete one. But anyway, this is what the JPEG algorithm does. It's a Fourier transform. So just wanted to mention that. And again, deterministic encoders are very good. And if you try to add randomness, it doesn't help. So let's look at the proof very quickly. So we can think about the problem in a slightly different way. Because the encoder is deterministic and the decoder is deterministic, that means that yn actually cannot take many values. The only values that the sequence yn can take are these values. So g of the integer 1, so g is the decoder. So g of 1, g of 2, and g of 2 to the nr. So these are the only. You can have many possible strings xn, but not many possible strings yn. You have to choose very wisely which are going to be your candidates, I call them, candidates, possible values of yn. And so the idea that Shannon had is that let's try a different value, let's say potential candidates, and then choose the best list of candidates. So I'll make this a bit clearer. So you take an encoder, a decoder like f1, so fn1 and gn1, and you try them and you see how much you get in terms of expected distortion between xn and yn. And then you do the same for several other pairs. So you have fn1, gn1, then you have fn2 and gn2, and you have fn3 and gn3, etc. And then you look at the average. And now the idea is very, let's say, a simple idea is if this average of the expectations is less than d, the target, the goal, capital D, then for sure, at least one of them, one of these expectations is going to be less or equal to d, because everything is non-negative here. So the idea is I might not know exactly what is the expectation for a given choice of G and F, but I might be able to know that at least there exists a good G and a good F somewhere in this family of choices. If I know that the average is less than D, then at least there exists one choice of Fn and Gn that is good. I might not be able to know which one, but at least I know there exists one. And that's all that we need, essentially. We're going to just prove the existence. Um, so maybe I just want to pause to, does someone, like, did you kind of understand the idea roughly of what I want to do? Or are there any questions? Okay, then yeah, so then the next step is this argument that if the average is smaller than D, then at least one is smaller than D. You can also apply it in a slightly different way by changing the weights in the arithmetic average. If you put any weight, that's sum to 1, so the pk is sum to 1, then again we have the same argument. If the average is less than D, then at least one of them is less than D. So what then you can say is, oh, this looks like an expectation of this quantity. So uh, and looking at this as an expectation will simplify the computation a lot. It will make things very easy. So let's try to write an expectation. So to be able to write an expectation, we need some distribution. So let's take some distribution over xy, whatever it may be. And then essentially we're going to choose some encoder and decoder and encoder. So choosing the decoder is like choosing the candidates. So that's why we start by choosing the candidates, which means choosing the decoder. So you're going to choose several possible decoders. Not just, let's say, not just one decoder. So it's going to be a random variable that will have some distribution. It can take value gn1 with probability p1. It can take value gn2 with probability p2, etc. So let Cn be this set of candidates to the NR candidates. This, as I said, this is all the possibilities for what the decoder can produce. So you have a family of candidates, but then this family can, as I said, take value 1 with probability p1, value number, another list with probability p2, or another list for probability p3, etc. And here, this is a specific distribution that we're going to use, but it doesn't exactly matter, like, for now. So as I said, this is about choosing the decoder. And now this is just choosing the encoder. I'm not going to get into the details, but let's say that for some choice of candidates, some list of candidates of 2 to the NR candidates that I call Cn. It's like a realization of the random variable. This is a random list, and this is a realization of this list. So for a given Cn, you have some encoder that's going to take the initial sequence and compress it into, map it into an integer m. Okay, so now, as I said in the previous slide, we look at an average of this performance or expected distortion. So you have an average now because we replace the P1, P2, Pk by this expectation, and we still have the same thing, which is the performance, meaning expected distance or distortion between xn and yn. So this is just a notation for yn. Is you go in the list Cn and you find the item number Fn of this is the integer small m that is produced by the encoder. You give it to the decoder, so you give it to the list Cn and you take the element corresponding to that index. So anyway, this is just the distortion between xn and yn. and we're just taking an average. And the goal, very simple, is if we can prove that this average is less than D, then that means that at least one realization of Cn, so there is at least one list of candidates that is good, that gives an expectation less than D. So again, if the average is less than D, then at least one of them is less than D. And so actually, if you look at the specific distribution and the specific choice of Fn that I didn't exactly tell you about, and you can actually do the computation pretty easily. I'm not going to show the details, but um, it's, um, it's very simple because you have an i.i.d distribution xn and everything is going to be i.i.d. Is rather simple. Just trust me.
So
I just want
sorry.
to. Yes, yes, go
So
ahead.
here the R is fixed or not?
Yes, yes, good point. So for now, what I've been telling you about is let's assume that we have R that is fixed, and we just want to try to reach uh, to have this expectation less than D. And then once we know, uh, let's say if it's possible, it will tell us which, if R was possible, actually, if R was a good choice. And
Ah,
while
yes.
computing this expectation, it will depend on R. And based on the value that you find, you will be able to know, okay, which value of R is going to be suitable to get an expectation less than D, and which value of R is not going to be suitable, and you can find the smallest value of R, which is our goal. This all comes from the computation of the expectation, which will give a result that depends on R. Um, yeah, know if you have any further questions. So yeah, so the problem could have looked a bit complicated at the beginning because the number n might be, so designing specific function fn or gn might be very complicated. But what we do is that we don't even worry about this complexity by just taking an average over all possible fn and gn essentially. Some, specifically about on all possible gn, to be more precise. And the average is actually very easy to compute. So it's very hard to construct, to produce one function fn, one function gn. That's tricky. But just computing an average over all possible choices is actually not that hard. That's the whole idea. Okay, and actually, now I just want to give you uh, some additional remark. I have hidden a little bit a small difficulty, which is that it's not enough if you want to find the exact like optimal value of R. Just look at the expectation of this quantity, but it might be important to look at uh, the distribution of this quantity. So as I said, you have the candidate Cn, the list of candidates Cn. Think about the average or the expectation over Cn, but we can also just look at the distribution. So this is a real number, which is inside the first expectation. So the second expectation gives a real number. Instead of average. So if you go and look at the distribution of this real number, which is inside this expectation of the distortion or distance, the thing we were going to be interested in is it possible that it's going to be bigger than D? How probable is it? If it's a probability that is less than 1, strictly less than 1, then we're going to be happy. Why? If this is strictly less than 1, that means that this event does not always hold. That means that there is at least one choice for Cn, so one choice for the list of candidates that will give an expectation less than d plus epsilon. So again, if the probability is strictly less than 1, then there is at least one choice of Cn that will give less or equal to d plus epsilon, and we will be essentially happy. So I'm not getting into the details, but I just wanted to say that's actually what we do. That's all I do in all my work, is to upper bound such a probability. And actually, it might look like it looks very complicated, but I just want to remind you what we're talking about is just, this is just yn, so it's a reconstruction yn, and the function d. I don't remember if I think I showed you at the beginning, but anyway, function d is quite simple in the sense that d for a sequence xn and sequence yn is just the average. So distance between xn and y1 plus distance between x2 and y2, etc., and you take the average. And now, proving an inequality like this on probability of an average bigger than something is actually something that is quite let's say, well studied and easy, uh, in the sense that if x1 to xn are i.i.d, and somehow you manage to have y1 to yn also i.i.d, then if you have an average of i.i.d numbers, so independent and identically distributed, then you kind of know where this is going by the law of large numbers. It's like if you do a lot of coin tosses of the same kind of distribution, then the average you will obtain is well known, essentially. We know what will happen when n is large. So to study this kind of probability is what we call in general using a concentration inequality. So concentration means essentially the law of large numbers. So essentially there are many tools to do this. Like is really not difficult to in general. Like if you want a simple bound, it will usually be very simple when you have a sum of i.d variables. For example, there's Höfting inequality. Or anyway, it's not very important, but I just want to tell you that this is what I have to sweat on. Like, this is the difficult part, is okay, I need to prove this, some upper bound like this. And what is nice is that because we are looking at extent that is i.i.d or maybe a Markov chain, then there is essentially a limit distribution always. And the fact that it's i.i.d or Markovian allows us to use the law of large numbers in some sense, and concentration. So this is what makes it quite easy to get these kind of bounds. And therefore, this will really allow us to find, the best, by finding the best possible bound, the tightest possible bound, you will have the chance to find exactly the value of R that will make this strictly less than 1. If you have a very good, very tight bound, it's going to be possible. So yes, so essentially that's the main thing that we have to do in this for these problems. I have skipped most of the details of this proof, but yeah, I think I just wanted to give you the main idea. I just want to, let's see, actually, how much time do I have? Oh, okay, so time has flown very fast. So I wanted to tell you about my favorite concentration inequality that that comes from information theory that I use. But maybe I don't, it's not very important anyway, and I don't have time to cover this. So, okay, so I have covered the traditional, the first problem that Shannon looked at. But more recently, I think from the 1990s, there's been a new problem um, that has been proposed. And essentially my work will be has been to work on that problem and improve it, or let's say modify it. Um, okay, so I'll present you this problem, and then maybe I guess we can take a break. So hopefully this will be more quick. Um, so I will just use the distance between distributions. So actually, because I'm looking at finite set X, uh, any distribution is just a vector. So you can just use the one norm, a simple uh, like L1 distance um, for a real vector space. Usually people divide this by 2, but really it doesn't matter much. Anyway, so just to say that I'm going to use a distance between probability distributions. So the traditional problem I showed you before, I just copying it here. You have this constraint that you want, when n is large, you want the expected distortion to be less than d. Here I put delta, but it's the same as capital D before. And the goal was, okay, I just want to target distortion, let's say 0.4 maximum, so that xn and yn are close, are not too different. And I wonder what is the smallest value of r that can allow me to do this. But it was really focusing on only on the distortion. And this has a problem. So if you focus only on distortion, it's the right side of the image, something that resembles JPEG. It will give something that is pretty blurry sometimes, especially if you want to compress more. And what people have done recently is say, no, we don't want anything blurry. Yes, we want to compress, we want to remove information, but we don't want anything blurry. So what they do is that they remove information like before, they do compression, but then they add details like photoshopping or filtering in some sense. So they use a generative AI, like let's say algorithm, to do this. So it looks very beautiful, but is still possible to compress and remove information as long as you add details at the end to make it look good, then it works. But unfortunately, um, this will not be possible with the same value of r than before. This trick has some disadvantages. You need more r, so you need a larger r, you need a bigger file size to be able to reach this. And I just wanted to tell you that, yeah, this is what is shown on the second figure, that unfortunately you have to sacrifice something. So this MSSSI on the x-axis is just the distortion. It's just the distance that we've seen before. And on the y-axis is some measure of visual quality. So this has, let's say, uh, um, very good visual quality, so a small error in some sense, so it will be low on the y-axis, and this has is blurry, so it has a bad visual quality. It's going to be high on the y-axis. And so when we look at many attempts, many algorithms, we notice one thing is that if you want to improve the visual quality, you have to sacrifice on the distortion. There is no choice. And same, if you want to reduce the distortion, you have to sacrifice in the visual quality. So the previous, as I showed you, this paradigm, this goal, it was just to focus on distortion, on minimizing distortion. This is not a good idea. If you just minimize distortion, you will sacrifice on the perception or visual quality. So this is why we changed the formulation of the problem by adding one line here, one constraint, with a distance between two distributions. Between the distribution, so pxn actually is just to denote the i.i.d distribution of the sequence xn, and pyn is whatever is the distribution of yn. So we want these distributions to be close, and this is linked to visual quality in the sense that if it seems if this is very small, if the distance is very small, then it will seem like yn comes from the same distribution as xn. And if it comes from the same distribution, then intuitively it should be as beautiful as xn was. That's the main idea. Yeah, I just want to say that sometimes, I mean, or very often we use capital pi equal to 0, so we require that distribution of yn be very close to distribution of xn. Um, okay, so this was the new problem that has been considered. And just to quickly wrap up on this, it is very different because now randomized encoder and decoder are necessary if you want to achieve uh, this last constraint that I showed, that distribution of yn be close to distribution of xn. Why? Is because the idea is the encoder is going to remove information. So there are a lot of possible values of xn, but not many possible values for capital M, for the message M, or the, let's say, the integer M. So if you remove information here and you do a deterministic map, even if it's a bijection, even if it's injective, you cannot have many possible values for yn. So if you have a deterministic map, you have only 2 to the nr possible values for yn, if there are no duplicates. So it's going to be much less than the value for xn. So if there are not many possible values for yn, it's not going to be possible that the distributions are close. So that's why, in order to increase the number of possible values for yn, we're going to take the message m, or the integer m, and then apply a randomized, so a not deterministic operation, and this allows to add possibilities, like the same value of m, because it's not deterministic, the decoder is not deterministic, then the same value of m can be mapped to 2 different possible values of yn. So this is how, from a small number of values of m, we can get a lot of possible values for yn. So yeah, I've written it here formally. The number of possible values is what I used like when I talked, but we can also use the entropy to make the same argument as what I just did. But anyway, I think hopefully I tried to explain correctly what the problem is. So anyway, it's a very surprising problem, and actually this is why I wanted to change it, because it's very, very weird. You compress an image into a file, zeros and ones on your computer, and when you open the image, you don't always get the same thing. Sometimes you get a certain value of the new image. Sometimes you get a slightly different one with slightly different pixels somewhere. So every time you open your file, you get a different output. This is something that I found very weird, but from mathematical point of view, in this new problem, you need randomization, especially at the decoder. So yeah, this is one of the reasons I wanted to change this problem. One last thing is, I said randomness, but there is something that is a bit particular. It's called common randomness. So this is this variable j that is shown here. So usually when you use randomness at the decoder, then the encoder does not know what is the value that you have used for the randomness. For example, if you flip a coin to make a decision at the decoder, usually the encoder doesn't know what you did. But common randomness is just a way to formalize that actually they know. Somehow they have access to the same information, and when the decoder flips a coin, you can do the exact same operation at the encoder, and you know, or in other words, you know the result in advance. And like we found before in the previous theorem, we have a new theorem now, where now you have the minimum possible rate to achieve distortion delta and to achieve this capital pi, this the distance between probability distributions should be less than capital pi. So we have a new minimum rate that is bigger than before. Unfortunately, you have to sacrifice something, but it still has this kind of elegant expression with the mutual information. But this elegant expression requires the amount of common randomness, or the value of RC, if you will, the number of possible values of J, to be very, very, very large. And this is also something that is not possible to do in practice. That's another reason why I wanted to change this problem, is because it doesn't make, I mean, it's not possible, it's not practical to, if you want to reach the optimal performance, you need specifically common randomness, not just randomness at the decoder, you need common randomness to get the best performance, and you need an insane amount of common randomness. So yeah, so this is what I just summarize. I don't think that this formulation is practical. I think that humans actually can judge a single image or a few images, and they don't need to look at the distribution. And also, the amount of common randomness should be reasonable so that it's possible in practice. So yeah, so this was the goal, and now I will give you what are the tools that I use in sections 3 and 4 to be able to change this problem, to define a new problem and study it. So maybe we can